Hello, in this video we're going to explain how we performed practical exercises 1 and 2. Hope you enjoy. In this first part we're going to talk about the basic elements of digital electronics, the logic gates. First we're going to talk about the binary numbers. The binary number system plays a central role in how information of all kinds is stored on computers. The binary system works under the exact same principle as decimal, only it operates in base 2 rather than base 10. A truth table is a diagram in rows and columns showing how the truth or falsity of a proposition varies with that of its components. Here you can see two examples of logic gates, where the output is based on the type of logic gate used. Logic gates are the basic building blocks of any digital system. It is an electronic circuit having one or more than one input and only one output. The relationship between the input and the output is based on a certain logic. Based on this, logic gates are named as AND gate, OR gate, NOT gate, and so on. At any moment, every terminal is one of the two binary conditions, low or high, represented by different voltage levels. Here you can see the 7 basic logic gates. They are AND, NAND, OR, NOR, NOT, and XNOR. Now we will see the results from part 1, 2, and 3, where we use different IC numbers and the type of logic gate.
In the second part, we are going to build a half adder and a half subtractor to show how binary addition and subtraction can be implemented with ICs. We will also build a simple digital memory called SR latch and another digital memory unit called JK flip-flop to observe the difference in basic memory function. A half adder is a type of adder that is able to add two single binary digits and provide the output plus a carry value. It has two inputs, A and B, and two outputs that are called sum and carry. We will use an AND and XOR logic gates. Here you can see how binary addition gives you the carry and the sum. As well, you can see the structure of the half adder and the truth table for it. The half subtractor is a combinational circuit which is used to perform subtraction of 2 bits. It has 2 inputs A and B and 2 outputs that are called difference and borrow. We will use AND, XOR and NOT logic gates. Here you can see how binary subtractor gives you borrow, and the difference. As well, you can see the structure of the half subtractor and the truth table for it.
The SR latch is the most basic type of a memory circuit. It stores a binary piece of information, either high or low. Anytime you set a latch, the output Q goes high, and anytime you reset a latch, Q goes low and Q next goes high. SR latch is created with two NOR gates that are connected. For SR latches, the output will change whenever the input changes. The input state is illegal if you press set and reset at the same time. Here you can see the structure of the SR latch. As you can see, the output of one NOR gate is the input for the other one, and vice versa. We also have the truth table for the SR latch. The JK flip-flop is a more complex memory unit than the SR latch from before. JK flip-flops are a memory unit similar to SR, but they're controlled by a clock. It has two inputs, J and K, and two outputs, Q and Q next. A major difference between the SR latch and the JK flip-flop is that the JK flip-flop has no illegal input state, even when both inputs are set to high. In order to get results, the clock is set to 1. If the clock were not set to 1, nothing would happen and we would remain in memory state. Here you can see the truth table for the JK flip-flop. And here is the characteristic table for the JK flip-flop. To begin with, both J and K are connected to ground, so when she turns on the clock, there are no changes, so we have the memory state. Now she moves K to the VCC, turns on the clock, and Q next is a 0, so we have the reset condition. Now she moves K back to ground, and J is moved to the VCC, and Q next is a 1, so we have the set condition. Now she moves both J and K to the VCC, turns on the clock, and we have the toggle state.